Okay, so hello and welcome to our next video lecture for today. So this time we have another problem on statically indeterminate members. So again, statically indeterminate members, you cannot just rely on the three equilibrium equations to solve for the unknowns here because it is no longer sufficient. So it must be supplemented by the behavior or the final position of the member subjected to the loading. So for this particular problem, we have here a weight supported by two bronze rods as well as steel rods. So they are coinciding or meet at one common point. So we can do it by joint method, by and then proceed to the final behavior of this. So of course, these three rods will certainly stretch because of the weight W. So given the uniform area of each of the rods, 495 millimeters squared, as well as the applied load 15 kilonewton, with the modulus of elasticity for each of the material, steel and bronze. So we are required to determine the stress developed on the steel rod, the bronze rod, and the displacement of the pin connection where the three rods met at point E. So for the first requirement, as a solution, of course, as usual, we are going to establish this free body diagram by joint method because all of the forces are concurrent at point E. So let us label this. And we have here the downward force weight. See, this is the P of bronze, P of steel, and another P of bronze, resisting the weight. So each of those has an inclination with respect to the vertical, 29 degrees. So by FBD or by free body diagram, we can see that summation forces vertical is equal to 0. So basically, there are three upward forces here. First, PB will involve a horizontal component as well as the vertical component. Okay, so we can just say that PB here, or perhaps we can start with summation forces along the vertical axis. You can say that W is just equal to a vertical force PS plus two vertical components of the bronze rod. So we can write that as PB cosine of 29 since the component is adjacent to the reference angle. So let this be our first equation, and this first equation will be supplemented by the behavior of these three rods after the load is applied. Okay, I'll just copy this one. So as a matter of procedure, we have discussed that we are going to unpin this joint at A. And then of course, it's obvious that these 3 rods will just stretch out. Okay, so let us have the corresponding stretches of these 3. By the way, we cannot compute yet the deformation since the forces are unknown. So steel bar will just stretch out as it is along its vertical axis. Same true with the bronze rods. Okay. So they have symmetrical orientation. We see. Let's zoom this out. Say this is the stretch in the bronze rod, delta B, and the center is the stretch at the steel rod. So the next step is to, of course, create a perpendicular line on this and then determine the location of the point where they commonly meet. And obviously, illustrating here a perpendicular line. Okay. So let's have a perpendicular line here and another perpendicular line on the other side, and then just enclose this one because they are connected. Okay, so let me have this perpendicular symbol here, and so for this one. So by this we can now form the right triangle relating delta B to the deformation of the steel. Actually, deformation of the steel is the hypotenuse common to the right triangles both sides of the equation. So by that, we can relate them by function of cosine. Function of cosine, we are going to utilize this angle. Of course, this is 29 degrees. So we write now the function of cosine. Cosine 29 degrees. Adjacent to that is delta of bronze all over delta steel. Okay. And then by cross multiplication, we can say further that delta steel times cosine of 29 degrees, this shall be equal to delta of bronze. So let us substitute the formula for deformation, PL over AE for steel. Okay, just write the equation. PL over AE for the bronze. Okay. So further, again, do not cancel this length here because they have different length. The bronze is actually longer than that of the steel. So we'll just proceed to further expand our equation and then come up with the relationship. Okay, so this is PS, this is length of steel, and the area, I think they have a common area of how much? 495 millimeters squared. Okay. So P of bronze, length of bronze, ayun, lagay rin natin yung kanyang modulus of elasticity. So modulus of elasticity for steel is 200 and for bronze is 120. So we write here 200,000. Okay, this is multiplied by cosine 29 degrees. Similarly, we're going to do that here. We have here 120,000. Okay, so let us determine the length here. No problem with the steel because steel has a length of 3,500. For bronze, it is just the hypotenuse of the right triangle. So relating the lengths of steel and bronze using the 29 degrees and 3.5, we will just use cosine function again. Cosine 29 is equal to, adjacent to cosine is the length of the steel all over the length of bronze. So substituting further, we have here 3,500 times the length of bronze. Okay, so by cross multiplication, derivative of the cosine 29 degrees, we just have the length of bronze is equal to 3,500 all over cosine of 29 degrees. So that is, let us compute that one. We have equivalent for 1001.74. 1001.74 millimeters. Okay, so let us carry that one. Okay, so we then substitute. So PS times 35 cosine of 29 all over 425 times 200,000. This is equal to E of bronze. The length is 1,001.74 cosine of, wala nang cosine dun, divided by 495 times 120. Perhaps you can cancel this 495 because it is just common to them. So here we will be having a relationship between PS to that of PB. We have here equal to 2.18 PB. So this is the relationship between the two. Say I'll have this to be another equation 2. Okay, so with this we can now go back to the first equation because we have two equations with two unknowns. So I'll just carry this one again. Okay, so this was the first equation. So we're going to have here W. So I think W is also given. So W is 15 kilonewton, or that is 15,000 newton. So let us substitute that one. We have 15,000. Okay. So PS is PS, and then PS is 2.18 P of bronze plus 2 PB cosine of 29 degrees. So in here we solve for PB. So we have 3817.53. This is in Newton. So solving for the corresponding P of steel, so you just have to substitute it in the original equation. So we have 15,000 is equal to, you just have to equate it in that equation. So we have P of steel is equal to 2.18 of 3,817.53. So P of steel therefore is 8,322.22 newtons. Okay, so with this, we'll now solve for the stresses. Okay? The stresses is just equal to the unit loading divided by the cross-sectional area. So sigma is equal to P all over E. Okay. So for steel, we have sigma steel P over A of steel. So sigma of steel is equal to the P, computed P is 8,322.22 all over the cross-sectional area, which is that is 495. And then for bronze, okay, we have sigma of bronze. This is equal to P over A of the bronze rod. So sigma of bronze is equal to computed one 3,817.5 0.53 all over 495. Okay, so we compute. So we have 16.81 megapascals, and for the bronze we have 7.71 megapascals. Okay. So that's it for this problem. And then with regards to the stresses, we have already solved that one. And then for the displacement of the pin at connection with the three rods met at point A, simply refers to the delta S. Okay, it simply refers to the delta S because A will just switch to certain position here, okay, and that is equivalent to delta S. So delta S is PL over AE of the steel. Okay. So we can just say that delta here is equivalent to delta S, PL over AE of the steel. So P of steel, or perhaps you can have this as sigma. Okay, so sigma steel is 16.81 times the length which is 3,500 all over the modulus of elasticity. So therefore that is delta S. We have 0.29 millimeters. Okay. Okay, so moving on to the next problem. So this time we have four bars actually to support this weight here. So let us label this joint. So this is A, B, C, D, and E. So if you notice the orientation of the bars is no longer symmetrical, just like the first example we had. So therefore there will be a tendency for this setup to move sideways. So what is good on the first example we had is that is symmetrical. So therefore the stretch will be concentrated only along the direction of the weight, and that is the vertical. So this time, since we do not have any uh, equal angle here, the tendency is when the W is applied, it will tend to move sideways. That is why we have here another bar attached to it to control the sideways movement of these bars. So anyway, the procedure is just similar, wherein we will just have to have the free body diagram of this, and then by the elastic deformation as for the behavior of these three bars when W is applied. So again, I'm going to have here, sorry, duplicate. So working on the free body diagram, see this is A, B, C, and D. Okay, this is W. Okay, so for this, we are going to place here the corresponding forces. So we'll just have to trace all of this. So those will be upward forces. So I'm going to label this as PAD. This is PBD, and this is PCD. Okay, so by summation, forces vertical. So we have P. So we have PAD going upwards. Of course, this is times cosine 43 plus PBD plus PCD cosine of 29 degrees. So minus W is equal to 0. So I think we have a given W here. So it supports the weight of 60 kilonewton. We'll just have to reflect it in here. So 60 kilonewton, that is 60,000 newton. So is equal to 0. So we'll just have to copy this one and then we transfer this one to the right side of the equation. Becomes positive 60,000. So let this be our first equation. So next, the second equation, as usual, will come from the behavior when the load is applied. So we may borrow again here a figure. So tingnan natin kung anong behavior. So I think we will have a similar orientation as the first problem. Ito, hahaba lang yan. Of course, this will elongate also along its direction, and this one will elongate also along its direction. And then make a perpendicular line, extend that one there, and then this is perpendicular line also. So all of this will have a common point. So we'll just label the deformation. This is A, B, C, D, and E. Therefore, this is delta AD. So this is delta BD. And this is delta CD. This is the 45 or 90 degree angle. So we just have to project the angles here inside the triangle. This is 43 degrees and this is 29 degrees. So as usual, we are going to have the relationship with the first triangle at your left portion. We will write cosine 29 is equal to delta CD all over the hypotenuse delta BD. So by cross multiplication, delta BD cosine 29 is equal to delta CD. Okay, and then we apply. This is PL over AE of BD cosine of 29 degrees is equal to PL over AE of CD. Okay, so we'll just have to substitute the data here. This is PBD. So what would be the length of BD? So here, BD has a length of 3,000 millimeters. What about its area? So on the problem, we have an area, same area for the bars, or similar areas for the bars, each having 490 millimeters squared, and the same material, which Young's modulus of elasticity is 210,000 megapascals. So 490 and 210. So we have here 490 times 210,000. So don't forget to write this. So PCD. So CD will utilize this right triangle to solve for the length of that CD. So again, by cosine function to relate both length, we have length of BD all over length of CD. So length of BD is 3000. So therefore, length of CD is equal to 3000 divided by cosine of 29 degrees. That is equal to 3430.06 millimeters. So to avoid that further disturbances by and by, we'll just compute for the other length, that is length of AD. Again, that is obtained by writing cosine of 43 degrees. This is equal to length of BD all over length of AD. So therefore, length of AD is simply equal to, see, this is 3000. So 3000 divided by cosine of 43 degrees, we have 4101.98 millimeters. So here, I'm going to carry that value. So we continue with this equation. We have 4101.98. So we have similar material. Okay. So I think that will just be cancelled there. And then we will be having a relationship between PBD in terms of PCD. We have 1.56. PBD is equal to 1.56 of PCD. Okay. So again, this is another equation. See equation number 2. So if you recall, our first equation contains here 3 unknowns. So we have 2 equations obtained from this, and I think another equation could be derived on this other triangle which contains 43 degrees angle. Okay, so the third equation will be coming from that one for us to work out with the unknowns. So again, here it is. We have to write cosine of 43 degrees, that is equal to delta AD all over delta BD. So by cross multiplication, we can say that delta BD, cosine of 43 degrees, is equal to the deformation along AD. So PL over AE of BD cosine 43 is equal to PL over AE of AD. Okay, so just the same, we'll have the relationship between the two. So PBD, okay, what is LBD? L of BD is how much is that LBD? 3000. So I think we can cancel this denominator since they have the same material with the same cross section. So this is equal to, sorry, still have to write that cosine 43 degrees, and then we have here P AD. What is length of AD? That's 814,000. 101.90. So this one. Okay. So again, there will be a relationship between PBD and PAD. So we have 1.87 of PAD. So let us check that one. For 101.98 divided by cosine 43 divided by 2000. So 1.87 of PAD. So let this be our equation 3. So let us have a recap now on what we have obtained out of this deformation. So first we have this one, PAD cosine 43 plus PBD plus PCD cosine 29 is equal to 60,000. So this is the first equation. Second equation, we'll just arrange it according to this arrangement. So we do not have PAD here, so that is 0. And then this is 1.56 PBD. Sorry. From this actually, I'll just transfer PBD to the other side. We have 1.56 PCD less PBD is equal to 0. So by that we can place here negative PBD, and then this is 1.56 PCD is equal to 0. This is the second equation. And then for the third equation, we have 1.87 AD. Okay, just have to write it in here, PAD. And then we transpose PBD to the other side, it becomes negative. And then we do not have any PCD here, so that is 0. This is equal to 0. We can now use three equations with three unknowns in your calculator. Okay, so we had the check this length of CD here misplaced. Just have to erase that one. So PCD times LCD, that is 3,430 supposedly. Okay, so anyway, we'll just have to replace our relationship. So 3,430.06 divided by 3,000 divided by cosine of 29 degrees, that is equal to 1.307. 1.307 PCD. Let's replace this one. Okay. Okay, so we'll have the same arrangement. We'll come up with the three unknowns arranged accordingly. If we are going to employ calculations by calculator. So we have 15,573.4 Newton, and then 29,122.26 Newton, and then 22,281.76 Newton. So knowing these three, we'll now proceed. We have to determine now the stresses in each rods. Okay. So for sigma AD, this is P over A of AD. So the computed value is equal to 15,573.4 all over the cross-sectional area, that is 490. So sigma AD is 31.78 megapascals. Stress at BD is equal to 29,122.26 all over 490. We have 59.43 megapascals. And for the stress at CD, 22,281.76 all over 490. We have 45.47 megapascals. So we have three stresses. So you might ask, what would be the stress on the horizontal member ED? So for horizontal member ED, all we need is to sum up forces horizontal to come up with the force or the corresponding force. So going back to our free body diagram a while ago, so here it is. So I'll just have to assume a horizontal force for that. Say this is P along ED or DE. So we'll just borrow this one. Okay. The summation forces along x is equal to 0. So we have negative P dE minus PAD sine of 43. Say another right words, PCD, so that is denoted by plus, sine of 29 degrees, so this shall be equal to 0. So we just have to substitute the values. PAD is 15,573.4, and we need PCD. PCD 22,281. 22,281.76. Okay, so finally, PDE is equal to 181.38 newtons. So maybe check that one. Okay, so it's really 181.38. So finally, the stress along DE is 181.38 all over 490. We have a slight stress of 0.37 megapascal. So this is the horizontal force, or meaning the horizontal member is having a slight stress only. So I hope you also experience the same, a slight stress in your subject. So this is it. This is the solution for this force members. So again, we would like to reiterate that the three equilibrium equations will now be supplemented by the elastic deformation, and then from that you just get some equations and work with that equation to solve for the unknowns. Okay, so our next topic would be thermal stress. Okay, so the thermal stress, let me have the notes here. So thermal stress is simply the stress that is caused by an increase in temperature. So remember that any material has a coefficient of thermal expansion. What is this all about? So if a material is subjected to an increase in temperature, it will expand eventually. Okay, so the expansion is dependent on the residual stress of the material. So yung bakan steel will have a different behavior on an increase comparing to an aluminum or a bronze material. So they have various values for the coefficient of thermal expansion, and also a certain drop in temperature will tend the material to compress, so kapag nag-cool down, it will shorten, so iikli yung material. So that is the principle. So in structural members, of course, there will be an allotment on this type of behavior. We allot spaces or clearances. We give clearances to joinings in structural elements and members. We allot clearances for a certain change in the length because of the temperature. As a practical example here is yung mga yung mga railings ng train railings. So this composes of steel material. So the connection hindi tutok yung hindi tutok yung mga railings na yan. May mga clearances yan or spaces in between in order to allotted for a certain expansion or contraction due to change in temperature. So you might ask, bakit naman yung sa reinforced concrete that composes of two material, right? Concrete and steel. Okay, paano kung may temperature drop or a temperature increase, biglang humaba, baka mag-separate yung bakal sa concrete. So that would be your question, So the answer is, kaya nga yung concrete tsaka steel is very compatible to each other, aside from the bonding of these two material with each other, is magkalapit lang yung coefficient of thermal expansion ng concrete to that of the steel. So that is the rationale there. So kung meron mang difference, then yung concrete or the bonding between the concrete and steel can tolerate that thermal expansion. Okay, aside from yun nga, malapit yung values nila, yung bonding nila is it can tolerate the certain change in length due to thermal expansion. Okay, so generally this material action will cause strain in the material where deformation is isotrophic. Yung ibig sabihin lang naman na isotrophic is that we have the same deformation in all direction. The element is isotrophic. Okay, so as a general formula, so we'll just have to focus ourselves in the expansion or contraction due to thermal change. So delta, so this is again expressed in delta, So delta T or deformation due to temperature is equivalent to alpha L delta T. So alpha L refers to the coefficient, what I'm talking about, coefficient of thermal expansion. That will be in terms of micrometer per millimeter degrees Celsius. And then L is the original length, and then delta T is the final temperature less the initial temperature in degrees Celsius. So by this, whatever that the temperature increase or drop, it will have a corresponding deformation on the thermal stress. And this type of stress is a residual stress because the material is not caused by an actual load, but it is a reaction of the material element with respect to the temperature change. Kaya nga tinawag yan na residual stress, kasi nga it resides within the material, but no external intervention or external forces that cause this to be stretching or contracting. Okay, so on our next meeting, we will have to go over with examples on this thermal stress. So as for your assignment, you should go over with these problems in advance and practicing as well problems on statically indeterminate that we have discussed a while ago. So thank you for listening. I hope you have a great weekend for today. Great weekend. Then have a more practice to improve yourselves. Okay?